Today we'll be presenting on the study that we conducted this past spring term at NASA Develop, which is a dual capacity building program in the applied earth sciences that pairs interdisciplinary research teams together with public and private project partners in order to conduct 10-week-long feasibility studies regarding environmental and public policy issues under the mentorship of NASA science advisors. So our team here today continued the work that was conducted by the fall 2020 term team out of the Idaho Pocatello node, which had partnered with Heath Hockenberry and Robin Heffernan at the National Weather Service Fire Weather Program, Mark Fitch at the National Park Service, and Dave Mueller at the BLM and NWCG. And our work was evaluating atmospheric mixing height estimations in the Western United States. Next slide, please. So for this study, we sought to assess the accuracy of National Weather Service mixing height forecasts through comparison with satellite-based estimates for wildfire smoke plume events in the Western United States. And this research was primarily motivated by the fact that Heath and Robin at the National Weather Service conveyed to us the fact that while there, for a variety of different reasons, there is inconsistencies nationally and interstate among the different agencies that compute mixing heights, and as well as the downstream agencies that use that information for authorizing no-go decisions for prescribed burns. So we really wanted to try and do an assessment here of those mixing height forecasts. And given that radiosonde data was not available for validation in this study, we based our comparative analysis on methodologies developed by previous researchers, Furon et al. 2015 and Fang et al. 2015, specifically applied to two satellites, Calypso Calliope and MODIS, to derive remotely sensed observations of vertical atmospheric profiles, which ultimately enabled us to assess the performance of the National Weather Service mixing height forecasts. Next slide, please. So we conducted this study throughout the Western United States across the years of 2006 to 2020. We mainly focused on the months of August and September, but expanded the scope to July for years when wildfire data was limited. And we began this study in 2006 because that was the year that the Calypso satellite was launched. Originally, this project focused solely on wildfire events in southern Idaho. However, our team expanded the study area to the Western United States in order to increase the likelihood of Calypso's transects intersecting smoke plumes and scale up the data inputs. Next slide, please.
Thanks, Dean. To give you all just an idea of our workflow for the whole project, here's a chart. On the left half, we have methods that we primarily explored and developed. So first, moving from top to bottom, we identified large plumes from 2006 to 2020 in the Western US using a suite of NASA Earth observation imagery, VIIRS fire boundaries, MODIS smoke boundaries, and then using Calliope and MODIS. So from Calliope, we're using the aerosol layer, and MODIS, we're using the water vapor profile, which we'll get more into those methods in a moment here. Wherever those satellites transected the plumes identified in step one, the large plumes from 2006 to 2020, we calculated mixing height. And so then the plan was to move into an intercomparison of those two methods with the Weather Service forecasts, which as many of you may know, are sort of composed of a few different components, including stall-based models, balloon soundings, and some forecaster expertise. And we scraped those values from the Iowa State database. Next slide. So the Calypso Calliope method, which we, or the first term dubbed a SmoCer. The aerosol retrievals from Calypso follow a sun synchronous polar orbit which is on a 16-day cycle. And so here we're using CLPSO's vertical feature mass, which is a level 2 product, to determine the maximum altitude of tropospheric aerosols in smoke plumes, which then serves as a proxy for mixing height. So the VFM, vertical feature mass product, is generated from a classification algorithm that utilizes aerosol backscatter to determine feature types and subtypes. An example of a type would be an aerosol, and then a subtype would be something like smoke. And those are the two categories, classifications that are most relevant to our work today. And as far as the resolution of this particular satellite goes, or this particular sensor, the horizontal resolution is 333 meters, vertical resolution is 30 meters within the closest 8 kilometers of the Earth's surface. And so, as in Fearon et al., which Dean mentioned earlier, and a couple other papers that have used Calliope data to determine mixing layer height or boundary layer height, we have removed elevated and discontinuous aerosol layers. And so one of the major limitations, and we'll get maybe a little bit more into this later, especially in the discussion, is but one of the very apparent limitations is the temporal resolution, which is 16 days. And so that was greatly limiting in what we were able to come up with, and sort of directed a lot of what where we ended up going with this study, was trying to maximize the data that we did have with Calypso. So anyways, moving on to MODIS. Jukes will take it away.
Thanks, Chris. The other method we use to estimate mixing heights uses MODIS vertical water vapor mixing ratio profiles to resolve the transition into the mixing layer and calculate mixing heights. Previous research showed that the vertical moisture profiles from MODIS agree well with the profiles measured from balloon soundings, and that mixing heights estimated from the two also agreed. So our team developed an automated script to pull these vertical atmospheric profiles that overlapped our smoke plumes of interest, visualize the water vapor mixing ratio profiles, calculate the gradient in the mixing ratio, and then automatically identify the inflection point in the gradient where the transition in mixing occurs. This method for calculating mixing height does come with some limitations. As you can see from these profiles plotted here, the vertical resolution is limited to only a couple discrete levels in the lower portion of the atmosphere. On occasion, there are also missing values, both spatially in the grid and in the vertical profiles themselves. But since the data files are produced for every 5 minutes throughout the day, it's possible to synthesize overlapping data from within the same hour to get a more complete data set. So this increased temporal resolution is one of the main advantages of using this method. In addition, we have temporal coverage from 2000 all the way up until present day. And furthermore, these data are available as a gridded data set, so we aren't limited spatially to satellite overpass transects.
So here, just going to take you through what a single sort of day looks like, a single day and a single fire weather zone for which there's a prediction from the Weather Service. So this is a case study for a zone in northern Idaho, shown on the left here, in the Calypso transect from A to A prime, going through that fire weather zone. And then on the right-hand side, we have the mixing heights that are estimated from our two different remote sensing methods, and then from the Weather Service estimate for that zone. And so we can see that, looking at the right-hand graph, that, well, actually, sorry, let me explain what the dots mean first. So just to clarify, the SmoC output, which is the Calypso data, these different colors represent different aerosol subtypes. So polluted continental, polluted dust, and smoke. The black dotted line is the MODIS estimate, and the red dotted line is the Weather Service estimate. So you can see that for this particular day, we are seeing that there's if we call the MODIS and a SmoCer estimates to be sort of correct, quote unquote, then the Weather Service would be an underestimate. So that's just like what one day would look like. And we'll show sort of what the whole study, which is composed of many, many data points like this.
And we're talking about being off by 1,600 feet between the two.
Well, this is in kilometers. And so I suppose.
Yeah, half a kilometer.
Yeah, could be. So between the red and the black, so the MODIS estimate for this region and the Weather Service estimate, that would be, yeah, it looks like around half a kilometer. As you'll see, half a kilometer is not so bad with respect to a lot of the data that we've collected. So yeah, we'll get to a larger comparison of the rest of them later. Yeah, any further follow-up questions on this slide? Okay, in that case, maybe just move on to the broader analysis.
Yeah, so moving on from this case study to a summary of all of our results, this box plot shows the distribution of mixing height estimates that were retrieved with each method, and the diamonds represent outliers in the data. So one key takeaway here is that the distributions of SmoCer outputs and the Weather Service fire weather forecasts, the two boxes on the left, appear to be very similar. The spot forecasts seem to be slightly lower, and MODIS estimates are noticeably the lowest with a very narrow range and no estimates at all above 3 kilometers. Next slide, please.
Here are the results from the comparison of mixing heights estimated from each of the satellite-based methods compared with the National Weather Service forecast. So each of these points represent the mixing height forecasted for either a fire weather zone or a county warning area by the corresponding average satellite estimated mixing height within the same area. The blue dots here correspond to the fire weather forecast, and the orange dots represent the spot forecast. And points along the 1-to-1 line indicate perfect correspondence between the two estimates compared. Starting with the SmoCer comparison on the left, it seems to indicate that the mixing heights produced from SmoCer generally align with the National Weather Service forecasts. We do explore some of the variation here, which we'll talk about in a couple of slides. The MODIS results seem to show more agreement with the lower mixing height forecasts, but didn't produce any higher mixing height estimates for the events we identified, as Lauren mentioned. We have done some exploration into why this might occur. Our algorithm chooses the lowest altitude inflection point in the vertical water vapor gradients, which should correspond to the lowest moist layer, the mixing layer that's contiguous with the ground. However, it's possible that there are other moist layers that are not necessarily caused by local mixing, but potentially were advected into the area by winds. This would be more common in coastal environments where there's a lot of sea-land advection, but also possible in really windy landlocked regions like here out west. So it's possible that in certain cases, we may be detecting the advected moisture that could be lower than the mixing height. This plot now shows the comparison of overlapping SmoCer and MODIS estimates over our smoke plumes. This shows a similar pattern to what I just discussed. The MODIS estimates are constrained to low altitudes where there may be some agreement, but there's a spread of disagreeing SmoCer heights. And there seems to be a pattern in regards to the aerosol type. The zones with predominantly smoke classified aerosols seem to show the greatest disagreement, which could be due to the classifications in the data product used. The algorithm used to make those vertical feature masks tend to classify higher layers as smoke aerosols. There's also uncertainty in those classifications themselves. Without knowing the true mixing height values, it's more difficult to tease out what might be causing these discrepancies between the satellite estimates.
So just to take another quick look at the comparison between SmoC, which is the CLPSO data, and the Weather Service estimates, as you can see, they disagree quite frequently, but we think that there's a broadly positive relationship. There's some sort of ovular shape with increasing upper and lower bounds, and in fact, they do covary in a significant way. And a regression says that the regression is significantly different from a slope of 0. And so moving on to the next slide, we're sort of curious about what the disagreement looks like at different mixing heights and how do they disagree across mixing heights. So we found that both spot and fire weather forecasts consistently underestimated, or I guess overall underestimated mixing height. And so the median relative errors compared to the SmoC estimates is negative 13%. And the mean relative error is negative 3.34%. And so this underestimation is consistent with the results of Fearon et al., which suggests that the Stull method, which underlies the forecast, also tended to underestimate mixing height. And so as shown in this figure here, which on the left-hand side, on the y-axis, we have relative error compared to the SmoC estimates, and on the x-axis, we have the SmoC mixing heights. At lower mixing heights, according to SmoC, below 2.5 kilometers, we have a tendency to overestimate on the part of the Weather Service forecasts. And then as we move into higher mixing heights, 3 and above, the vast majority of the forecasts are lower than the SmoC prediction for mixing height. And so, yeah, moving on to the next slide.
So going back to our box plot with all the distributions, given the apparent differences between National Weather Service, fire weather, and spot forecasts, we also wanted to explore potential differences between these two types of forecasts where both were available for a given day and location. So here we plotted these forecasts against each other with a 1-to-1 line showing perfect agreement, and we can see that they generally do agree. The spot forecast was lower than the fire weather forecast in around half of these cases, as you might expect. But it's interesting to note that the points below the 1-to-1 line are typically farther away from the line. So while the spot forecast was never too much higher than the fire weather forecast, it was often much lower. Next slide, please.
So getting back to the question of relative error, which Chris was discussing 2 slides prior, we sought to explore the spatial trends and the mixing height comparisons between the National Weather Service fire weather forecasts, including both the zonal and the spot forecasts with the SmoC outputs in relative error. This map does not include the MODIS data and illustrates the percent relative error of the fire weather forecast in relation to the SmoC mixing heights, where each of the SmoC estimates were computed as averages across each fire weather zone, which are the excuse me, the light gray polygons depicted across the Western US here. And here you can see that the National Weather Service tended to underestimate mixing heights compared to SmoC in the Pacific Northwest, primarily, as well as in parts of Wyoming. But bear in mind that these results are based on data for just 51 fire weather zones out of the 411 zones across the study area, which is just 12% coverage. And we attribute the sparsity of data here to the fact that not every state in this study area is reports mixing heights. And also there were certain fire weather zones that either did not have mixing height data available, or there was just not a large intersection between the areas where we had calypso transects that intersected fire weather zone polygons that reported those mixing height observations. Next slide, please.
So to summarize our conclusions, we found that the National Weather Service fire weather forecasts and SmoCer outputs from Calypso co-varied positively and significantly, but there was frequent disagreement between these two estimates, and the Weather Service forecasts were often lower. MODIS estimates generally matched low altitude Weather Service estimates, but did not match high altitude estimates. And this may have been due to climate factors. And lastly, National Weather Service fire weather and spot forecasts generally agree, but the spot forecasts are sometimes much lower. Next slide, please.
And lastly, we'd like to just acknowledge all the different folks that helped make this study possible. Firstly, Brandy Nisbet-Wilcox, our Develop Fellow that provided a lot of guidance throughout the project, as well as the Fall 2020 team, which initiated the project listed under the past contributors, and our science advisors, all of which are present at this meeting today, as well as the project partners themselves, Heath Hockenberry, Robin Heffernan at the National Weather Service, Mark Fitch, and Dave Mueller. So thank you all so much for taking the time to listen to our presentation and for the invitation to talk here today. And we'd like to now open this up to a larger discussion where we can address questions regarding the content presented in these slides. And also the team has compiled a list of questions for the group as well, which we are excited to ask to a group of experts as we are currently pursuing a publication for this research in the Journal of Operational Meteorology, and are really looking for insiders' perspectives on the methodologies that we employed, as well as some of the major takeaways from this type of research that we could incorporate into our article. So yeah, without further ado, are there any burning questions?
Folks, great presentation, and thoughts from the SmoC committee.
Any thoughts on using or looking at turbulent kinetic energy over stall? Hello? Or did how come I always pose a question and it's dead silence? I guess I have that uniqueness.
No worries, Gary. Let them think a moment here. Come on.
Yeah. It's also, with four of us, it can be tough to, know who's going to speak up. But yeah, I suppose in the Furon paper, that paper does actually discuss this exact method as compared to the turbulent kinetic energy. And because we are not experts we had 10 weeks to come up with this project and didn't have, I think, the capacity to test out multiple methods, and B, because the turbulent kinetic energy I don't think performed any better with respect to the rate to this method, or really very differently with respect to this method compared to Stull. And so we just sort of went with Stull, largely also because the Weather Service already has these predictions which incorporate it into their forecasts. So that was the rationale.
Yeah, no problem. It's just that I guess from my perspective, and I'm not a scientist, but I'll ask questions. And this is Gary Curcio, but I was thinking that the indication was turbulent kinetic energy was the best at that time when Ferran did his paper. And with that said, I'm just concerned. I understand why we went with stall. It's easier. It brings in your capital investment on your Raywin sound stations and such. But I did pose it then, and I'll pose it now. Let's not. That's something to look at, the economics and your capital investment. But also, if you're going to spout out, we're going to use best science, then that tends to move the economic question and your capital investment out of the way in my book. So I guess it's just a thought or a comment that, we need to keep open minds and pursue what is best. And I think your work here is great. And it's just more evidence to me that, as I made a comment earlier, we need to be rocking on this because we really need to look at it. And we've been stuck in the Holsworth world for ages. And his science was good, but he was at the right place at the right time. And it was the only thing available. That's the way I look at it from a history perspective. And with that said, I mean, we really need to look at the whole picture of mixing height and transport wind and vent rates, and how do you classify how well the smoke will disperse. Again, a comment, but I'm curious, did anybody think about looking at Gary Ackmeyer's work with day smoke and the concept of multiple cores, which then takes in the heat effect of the fire, which raises the plume? So did anybody review his work on that? Because his day smoke model really, to me, was hitting the mark on how the plume actually performed.
Well, Gary, this is Keith Weber. This is actually the second term of this study. And during the first term of the study, we talked a lot about individual fire effects, and that a given fire that is burning over a very dry column of atmosphere, or burning under a very dry column of atmosphere, semi-arid areas like Idaho, some other fires giving off more heat, a more intense fire versus others, that can all have effects, we surmised. But over these 10-week terms, we did not have a chance to dig into that and do any research on that particular effect, though it's certainly something that we did think about, but I guess we probably can't answer your question any better than that, unless one of the other team members or Travis has some more information.
Yeah, well, just a comment again on day smoke and some prescribed fires that we did where the model was projecting plume rise to 10,000 plus feet, and the mixing height that day that I specifically remember was 6,000 feet. Well, we blew past the 6,000 foot mark and went to 10,000 feet, and that was verified by radar and by airplane. And all I'm saying is that the day smoke model in my book actually predicted how that plume was going to react with the meteorology at hand, whereas the forecast, as this study talked about, was grossly underestimated, 6,000 versus 10,000 foot.
Yeah, so you saw an actual mixing height of 10,000 feet. Was that from a spot forecast?
I'm sure we did have a spot, but it was also pulled from the National Weather Service fire weather planning forecast.
Okay, right. Thank you. Cool.
But again, Gary Ackmeyer came. I know EPA was looking at his work for a while, and I thought other scientists were picking it up. But I guess since Gary has been retired for some time, I really haven't seen much of that concept of day smoke moving forward. It seems to have, like other good research, it's now in the file cabinet.
I see. Yeah. Huh.
Other questions for the team?
This is Susan O'Neill. I've got a question about the Calypso data, and let's see, I'd be interested, or could you describe again exactly like how you use the Calypso data to get at the mixing height data? Because I think you're using the different aerosol types and the vertical mask feature mask. But yeah, if you could go over that again, that would be great. Because I was wondering, were you just looking at times when the atmosphere was smoky, or was it just lots of other times too?
Yeah, I can speak to that a little bit. Thanks for asking. And so first, I guess going to, we can keep it on this slide. What we started off doing was looking at throughout the study period from 2006 to 2020, visually identifying smoke plumes using a few different NASA Earth observation technologies. And so there's like the VIIRS data set. We used MODIS and Terra, and basically identifying where, relatively close to a fire, there were Calypso transects, and then specifically at what latitudes would those transects be intersecting with a smoke plume. And so in that stage, there's not really, in that first sort of step, it's basically just, there might be a little bit of non-smoke regions sort of on either side of the Calypso transect that we identified, but 95% of that transect is smoke. And then moving into the actual mixing height calculation, where we're using the maximum altitude of tropospheric aerosol as a proxy for mixing height. In that case, where there's no sort of tropospheric aerosol identified, that is not used at all in our data. So if it's sort of like clean air, we through Calypso are unable to actually come up with a mixing height estimate. This method has sort of been tested specifically in the context of smoke. And so our estimates are targeting that, are trying to estimate mixing height where smoke exists and where Calypso has identified like thick continuous layers of aerosol.
Okay, I see. So fundamentally, you're using the aerosol information from Calypso and saying that the highest point of aerosol vertically in the atmosphere is an approximate mixing height then. Would that be a correct interpretation or summarization?
Yeah, definitely. With a few sort of criteria attached to that, maximum height. But yeah, definitely that's a good sort of take home.
Yeah, okay, great, thanks. And then so if, so that being the case, sometimes, we know that smoke plumes can often go through the mixing height, go higher in the atmosphere if they're big and hot, they're pyrocumulonimbus, something like that. So did you try to identify and maybe filter out those cases so that you're only dealing with perhaps smoke that would be under the mixing height?
Yeah, we definitely tried. So a few of the different things that we're looking at were the level of the degree of detachment from the Earth's surface. So how is it separated by a kilometer, or is it separated by 5 kilometers from the bottom of the plume? So does the plume start relatively close to the Earth's surface? Is it completely contiguous? I'm not sure if either of those would necessarily speak to pyrocumulus, which obviously are contiguous. But I guess long story short, we tried the best we could, and we also went sort of in line with what previous studies have done, which we used the same sort of set of criteria. And so that was the extent that we were able to sort of get at that. And we could look into the actual profiles and see with our with a non-expert lens, sort of be able to judge, well, okay, this profile was thrown out. Does it seem like it should have been thrown out? Or this profile was not thrown out. Does it seem like it should have been thrown out? And so that was really the way that we went about it, was following suit with previous studies with their criteria for what should be what would be a good proxy for mixing height, and then going in and sort of verifying manually that nothing crazy was happening.
Mm-hmm. Yeah. Okay, thank you. Yeah, I know this data is not easy to work with. So yeah, I appreciate the analysis and thought that went into this. This is cool, because actually what's nice about this analysis too is that and this actually touches on a little bit of, I think, what Gary was getting at too, is that you're trying to identify a mixing height in the presence of smoke. And we know that our regular, meteorological forecast models are not accounting for the presence of smoke in the atmosphere, which can, change the results of a forecast, in terms of temperature and wind speeds, things like that. So, so this is interesting. Thank you very much. I had one more, I guess, another question, if I can keep going here. With the MODIS, well, I guess with both of these data sets, the MODIS data set and the Calypso data set, the processing that you're doing, do you, and this might be better fitted for the MODIS data set, do you, are you looking at trying to accomplish the processing in like a near real time type time frame?
So in terms of the MODIS data sets produced, we collected like historical files going back to 2006. With the quick release of MODIS data, it's possible that it could be done closer to real time. If the data is released like the day before or the morning of, it is possible to run that really quickly through our algorithm. With Calypso, there is a 6-month delay in the release of the data, and so that would not be possible.
Yeah, okay, great, thanks. Yeah, I could see a utility in a near real-time MODIS data set. So maybe that's something to think about. Yeah, thank you.
Thanks.
Other questions? If not, I have some.
Yeah, I got some more.
All right, you go, Gary, then I'll go.
Well, I guess first, I mean, as a group of scientists, I mean, and Susan backed me up on this, I mean, plume height achieved is, to me, is not mixing height as a burner. We may reach the mixing height that's been forecasted. We may punch through the mixing height that's forecasted. But when you got, horizontal wind shearing the smoke column, I would say on most prescribed burns, we don't reach that mixing height level that's been forecasted. So, it's kind of a conundrum. But as researchers, I would certainly, I don't know if it's a question versus comments here, but I certainly would include any fire, prescribed and wild. The wildfire usually is going to generate more heat, so you're going to get more plume rise. But with prescribed fire, we're burning under less intense, so less plume rise. And so that, but we need to know, that box of the mixing height of, what's achievable in the dispersion of the pollutants if we're doing prescribed fire that we have the capability of. And I'll throw this out, now we're starting to use dispersion models. And even though the dispersion models may be reflective of the mixing height within them, in the North Carolina smoke management program, mixing heights and transport wind speeds become obsolete if you're going to use dispersion model, because it's built within the dispersion model where you're dispersing your smoke. So now you're evaluating smoke impacts. I'm not saying that this work is not important. It is. But in relationship, are you going to, if you take this study further, are you going to look at prescribed fires? And well, maybe I'll stop right there. And will you include prescribed fires if you do this further down the line?
Jukes, I think you're controlling the slides. Can you go back to slide 11 and then display that up on the screen? Yeah, so while maybe the rest of the team is thinking about this. So Gary, I think this is what you were referring to, that if we look at these a-smoker point observations, sometimes the points are above the black line. That's where you had said that the mixing height punched above the forecast. In some cases, we see it below that line. Is that what you're referring to?
Yeah.
Yeah. Okay.
And again, you also have the conundrum of what's the fire doing in terms of heat production.
Mm-hmm.
It can get very intense. You have multiple, again, in prescribed fire situations, you're going to have a less intense fire, but sometimes it does get intense. And temporarily, I mean, I've been on burns where we did punch through the mix layer and you see a totally different smoke transport going on, and it could be short-lived, 30 minutes to an hour. And when the intensity of the fire dies down, then we stay within the mix layer of that smoke.
Yeah, I wonder, have you looked at some out here in the West? There's some slash piling and then burning of the slash piles instead of a more traditional prescribed fire. Do you tend to see more intense fires with those slash burns versus the more traditional prescribed fires? More heat produced?
Well, I haven't seen Western slash piles, but familiar with pile burnings that we've done here in the East, as in land clearing operations. They become more of a pollution hazard than anything else, because although the pile may be intense, with the humidity recovery that we have out here in the East, which is we'll shoot 80% or higher at night, that wreaks havoc in terms of smoke dispersion.
Right. Makes sense.
And if that pile is not super dry, and it's kind of difficult to get it there because we're not experiencing 12% RH during the day, maybe we got 40-45%. So we got a different animal that we're dealing with, and it really becomes a smoke issue with doing pile burning.
Right.
And it's really more, I want to say, almost regulated, because here in North Carolina, in the high hazard counties, which are your organic soil counties, you are the Forest Service will tell you how many piles you can burn in a given day.
Right. Okay.
And so it's very restrictive. And needless to say, much of that activity has really subsided from a historical perspective. There's not much land clearing going on. And this was during the push when a lot of the wetlands were cleared for agricultural purposes in the 70s and the 80s. But I did have another question, if I can. And when you looked at, you broke it down in very large groups of medium era and mean era. And I was wondering, if my memory banks served me right, I thought the National Weather Service criteria for mixing height was plus or minus 200 feet. And I don't know how they achieved that. They've never explained it, but irregardless, with that type of a 500-foot, let's say, swing of hitting a forecast or missing a forecast, would it be beneficial with the data that you already have to break that more down into a finer classification to see if there's a more so of an error, maybe by forecasts that fall within 1,000, 1,000 feet classes or something like that to look at the data that way?
Dukes or Chris, can you address that?
Yeah, could I just a clarifying question? So in terms of grouping it to something that would fall within, that 1,000 feet of error, you're talking about like looking at that data and doing what with it?
Yeah, I guess like if you grouped the mixing height forecast by a certain class, let's just say for arbitrary rate discussion here, you had from 0 to 1,000, 1,000 to 2,000, and so on. So you had 1,000-foot classes, and then all the mixing heights or forecasts that were classed in there, trying to differentiate what the error was by the class. So let's say, did they constantly blow when the mixing height should have been, from 3,000 to 4,000 feet? That was the group where they had the largest error in.
Right. Yeah. And so that is what this graph is trying to show a little bit here. So we have the remotely sensed Calypso on the x-axis in kilometers, and then on the y-axis we have that like relative error, which is a percentage of the Weather Service estimate. So you can see like from 0 to 2 kilometers, for example, they're like blowing it out of the water. It's like 300% estimate.
Okay.
So and then above 2, we're seeing that there's more of a tendency for the Weather Service actually to underestimate the Calypso derived estimates, if that makes sense.
Yeah, I'll have to study your graphs a little more, and I'm not quick on graphs, but anyhow, that's my problem.
Yeah.
So thanks, Gary.
This is Susan. With this graph that you're showing right now, I'm just curious, did you do a similar one where on the x-axis you use the MODIS data?
No, we did not. And we haven't yet explored having the forecasts on the x-axis either, but those are certainly things we can calculate going forward.
Okay, cool, thanks. Yeah, it would be interesting to see, yeah, kind of that whole suite there together and see if similar trends show up or not. So yeah, thank you.
Yeah, that would be really interesting for their analysis.
So what's the, for your data set, what is the distribution time-wise? What, starting June through September, July? I mean, what was the time frame?
So we've looked at any plume events from approximately July through September. Most were concentrated in August, and it varied, the magnitude varied by year. And I'd have to look back into the data to see if there's any trend annually.
Yeah, so there's probably something there, but also in your paper documentation, et cetera, you should make sure that you should classify that, because it gets a part of what Gary was getting into in terms of the potential implication or lack thereof for the other seasons where prescribed fire fits into the equation. So it just takes that dialogue right on out of the situation. Another question that I have is, you made a comment earlier on the map of the areas where you graphically displayed the Western United States. It would be valuable, since you mentioned it, if there were specific fire weather zones that did not provide mixing height, to document those explicitly. I'm kind of curious if this is constrained by the overpass as well, or what leads to the choice of some of those, because I know that mixing height is provided for a number of those areas, and so that there's not a misperception as to what's being represented there. Because if you use the whole West and this is what you could come up with because of overpass, because of availability of mixing height, boy, oh boy, that would be a large statement in and of itself. And so just, throwing some ideas there in terms of that distribution.
Yeah, that's a great point. Thanks for that. It would definitely be informative and to delineate those fire weather zones and even those states that don't provide mixing height forecasts. And we don't want to misrepresent anything here. So thanks for that.
The other thing that I'm thinking about also is in your methodology, did you with Calypso, did you do any assimilation of that or comparative analysis rather with miser data? And might that be useful?
What was the data that
MISR? Miser, it gives you plume height tops.
We didn't look into that, but I personally wasn't aware of that type of data set. Anyone else on the team could speak to whether or not that was something that was taken into consideration.
So this is Travis. I'll just jump in here. Miser would be good, but because of its orbit, we can't really, there wouldn't be a lot of collocations with Miser and Calliope. So MODIS well, it's not anymore, but it used to be on the same orbit as Calypso. So those were already inherently collocated. So that's one of the reasons why Miser, it's possible to get some collocations, but it would definitely be more limited.
Yeah, I guess it might build confidence in your methodology or not. I mean, just understanding what the differences are. There's a fair number of papers on the distribution of plume height from Miser with larger wildfires and may fit into this, into how you characterize the approach.
Yeah.
Just an idea. You were asking for ideas. So two other questions. Any plans for the rest of the West, kind of looking at that map, or looking at the East?
Yeah, how come we're always cut out? I'll say it. I don't like it, but I'll say it.
I can jump in real quick and say that these are all really great ideas for potential future projects. We've talked a lot about kind of future directions for this. The team, anyone on the team could potentially take it further if they're interested. It could be a great great thesis for someone, or it could be a potential future developed project. But currently, we're documenting all of these potential future directions in the paper, but there are no current plans for anyone to move forward with those at this time. But I think it would be a great idea for the future.
Well, I guess there's one working on a PhD. I think someone was at UW or something. So who knows?
Yeah, that's me.
Christopher, right? Okay. Well, you should reach out to Susan O'Neill. She's at the PNW Air Fire team and modeling smoke and satellite utilization. She's part of HACAST and a bunch of other things. So you may want to reach out if you have an interest in following up on this.
And I'll just echo that. Feel free to contact me. Yeah, I'm still here briefly. I'll have to run in just a moment, but yes, I'm here in Seattle, and so Christopher, if you'd like to talk at some point, be happy to meet up.
Great, thank you.
Sure,
appreciate it.
It's about connecting. So great. Other questions? I've kind of dominated a couple of minutes. Gary's been busy. Other questions from anyone else? Or
this is Susan. I have, I guess, one idea to maybe, and this would be adding to the list of potential work here, but for analysis, again, back to the MODIS. So you're using MODIS to estimate mixing height. There's also the MIAC data set that is a plume estimate, plume top estimate height based on MODIS data as well. And so I would be curious, I would be curious to see how plume top estimates might perhaps line up with mixing height estimates that you also get with MODIS. It could be an interesting analysis and might help also give some insights into using, the perhaps utility of using Calypso aerosol data from Calypso as a surrogate of sorts for mixing height too. So just a thought there.
Actually, what was that data set that you just mentioned?
The MAIC data set, MAICI, and the M is for MODIS, and I don't recall the rest of the acronym at the moment. But MAIC is a product, and it's an estimate of aerosol optical depth, and it also provides a plume top estimate as well.
Yeah, thank you for bringing that to our attention.
Susan, I got a question for you. Is Blue Sky doing anything with day smoke?
With day smoke, no, we are not right now.
Well, again, I think for all you researchers, it's intriguing, and no one has said why they're not looking at it, but I'd certainly take a look at Gary Ackmeyer's stuff. And for the research group here, were you in contact all in looking at the work that Tim Matheson was doing?
No, would you enlighten us with what that is?
Well, he helped me out, Pete. I think Tim's retired, but he started a project where he was actually doing radiowind sounds on prescribed burns, and he was actually opening up the burning program, I believe, in Colorado and other states in the West there, because he was the GAC meteorologist and for a while there, but he's retired, but I still think he's active in the study. And he was doing local radiowind sounds. And so he was turning no-go burn days into burn days because of the on-site weather and the instrumentation that he had, where he could demonstrate that the mixing was better than what was being forecasted, as your study has shown. And I just thought he's a meteorologist, he's a scientist, so he might be very insightful as a point of contact for your, if you want to take this work further, just to get concepts and ideas that, he's been addressing over the past 2 to 3 years. As well as
actually,
Jay.
Your leadership, Heath Hockenberry and Robin oversees, as you know, the Fire Environment Committee, and the Fire Weather Subcommittee, which Tim was part of, I believe. That was a project that was paid for by the National Wildfire Coordinating Group. And so there is some material. And so Robin's probably a contact point for some of the data and the specifics on that as well.
And I guess the person that's still more as well as active would be, maybe you already know, Jay Charney. Because I believe Jay was in consultation with, as Tim was doing his work, if I'm not mistaken, although I may be mistaken, but I think Jay Charney, and he's still active out of the Easton area consortium up in Michigan.
Yeah. All righty. Any other closing questions or comments?
Yeah, when we gonna rock and get this stuff working? I mean, time's a wasting.
That's a task. That's a task, not for the group, not for our presenters, but one we can follow up within the community, the SmoC committee call. Any other questions on the SmoC committee side?
Amen to that comment. All right.
Okay, well, I just want to say thank you, first of all, for doing the work, and nicely presented. I hopefully got what you were looking for in terms of ideas. I think you said something about slides of other directions. I don't know if that was something that you wanted to share, or if you were just looking for the input that you got, and hopefully that some of this was useful and valuable information. I think about some of the findings that you represented as actually something that has fire behavior implications as well as smoke as well. Greater height certainly has an influence there. So as we think about that, there's implications here. So I sure appreciate your time, effort, and 10 weeks of, if that's the duration of this effort. Hopefully someone takes and spends 20 weeks and gets even more. Any other closing comments from anyone else?
Yeah, I hate to be a pain, but I guess the other, also, we talked about prescribed fire and difference intensity of the fires. Like I said, I think your focus was on the, plumes generated by wildfires. They're going to be more seen. But the work done by Warren, is it Heidelman, Pete?
Heilman.
Where he worked with, I forget what model it was. I think it was Canopy for low intensity fires, which is very important, to our prescribed burning program. Wildfires without a doubt is a problem, but the prescribed fire brings different challenges to us, and we don't like to be shut down in prescribed fire situations. And that's why, like, North Carolina went to dispersion modeling, where I said it's irrelevant what the mixing height and transport wind is, because now you're evaluating smoke impact. So, we've burned with mixing heights by using high split, with a mixing height of, it was forecasted at 1,200 feet. Well, by the Clean Air Act, you don't burn under 500 meters or 1,700 feet for mixing height. Well, there we were burning at 1,000-foot mixing height. And it was all because we evaluated plume impacts downwind, and they were interpreted through the model as being acceptable. So again, I think this aspect of looking at prescribed fire and how the plumes go is very important too. And so please, if you go further with it, don't overlook that. It will bring a different host of challenges. But just as much as we are involved in wildfire, on the flip side, if we're not in wildfire, we're doing prescribed fire. So we need this information for prescribed fire as well.
All righty. Closing comments from the presenters?
Yeah, well, thank you all so much for your astute questions, and well as the comments and the discussion that was generated. Gives us a lot of things to think about for the future. And we did compile a list of questions, and we don't want to take up too much of everyone's time here, but there's a few minutes we'd like to get some of your expert input on some of these questions that we generated. And first, we wanted to ask about whether or not there are different methodologies employed for producing the spot forecasts than for the fire weather forecasts for the fire weather zones, and if there's any other things that could be going on that would produce that discrepancy we saw there, where the spot forecast tended to be lower than the fire weather forecasts.
Why the bias is what you're asking.
Yeah, and it could, I mean, I don't know too much about this, but it could be with something related to what Gary was talking about, how I think the fire weather forecasts were just produced for days, not necessarily in relation to specific fire events, whereas the spot forecasts are for specific fires.
Yeah, spots are tied to a specific time also.
More importantly, they're tied to a point.
Yeah.
A fire weather planning forecast, I don't know if this is the acceptable answer, but it's a zone, which usually here in the East, a zone is a county. So it's taking the average value for that county is the way it's been described to me. But then when you ask for a point, well, as I said, you're in a county, but now you're in a point. Well, do you happen to be at the high end where you're at the, the zone is that the fire weather planning is the average. So that's where the discrepancy may come in which is a built-in bias of just the type of forecast you're getting, where it's, could be covering here in the east a 500,000 acre county versus I'm only burning, 150 acres over here. And so I could be at the eastern end of the county versus the western end of the county.
Gary, your point is on. I mean, there is an averaging scheme that happens across the fire weather forecast. In addition, when in going to the point that, as you're describing, there is a timing specific issue.
Right.
And the spot weather forecast is a supervised product. In other words, it's not just plug and play. It's not relying on the averaging scheme across a topography range and across, there's a variety of factors that would contribute here. But I would think, based on that inclination between the fire weather forecast being a broad area and the spot being a specific, that you would see a distribution in both above and below, just based on the averaging scheme. But I don't know. That timing might be an issue. So understanding your spot weather forecast in terms of timing versus what the specific information is between, say, some fire weather forecast zones in the west are quite large because of their characteristics, and they do try to look at topography. So yeah, I'm not sure. A couple of ideas.
The other thing, Pete, is the bias of the forecaster themselves.
Yeah, there is that.
And whereas, as Pete said, it's the fire weather planning forecast, the zone forecast is more of a canned output, which is overlooked by the forecasters. Is it right? Versus the spot is now very specific and they're zoned in. And if you want to say there's more manual effort, oversight by the forecasters. So they're getting more detailed, whether it's for prescribed or wildfire, because now they're looking at a point on the landscape.
Not sure if that helped.
That's all very helpful. Thank you very much.
Other questions? I mean, we're okay with going a little bit longer. We didn't have a huge amount to cover within the committee, and not every day you get the opportunity to intersect. So if everyone's willing to stick it out for a few more minutes.
I guess it would be helpful to also understand from each of you a little bit more about how forecasters actually make mixing height forecasts and how it's generally standardized. I mean, I understand that there are different forecasters that might have different potential biases, but we were wondering if you could talk a little bit more about the standardization that I'm sure occurs across different agencies or counties, maybe through annual trainings or workshops or something like that.
I would say it's evolutionary, but I think that, what Gary spoke about before, which is the work by Tim Mathewson under the Fire Environment Committee, really got at some issues there. There is variability from forecaster to forecaster. There is variability by fire weather zone and by specific weather forecast offices. There's some pretty heavy variability. Gary, I don't know if you want to express, I think you might remember some of Tim's stuff, maybe not. But that would give you a documented place where there was specific outcomes related to differences in approach that are found within a weather forecast office and performance in the field. And that's probably going to be the most enlightening dialogue that I can think of that's documentable, rather than just supposition about how people approach stuff.
And like a couple of times I've mentioned North Carolina. Obviously, I'm in North Carolina, but because of an activity of certain individuals, what goes on in North Carolina may stay in North Carolina, like if you're in Las Vegas or something like that. But with that said, what I'm getting at is I know the forecasters, the 7 forecast offices in North Carolina are using as a cursory preliminary first look, in at least this is what I've been told by some of them, they're looking at the stall method, and then they go from there. Now, what does that mean? I'm not sure, but they're at least looking at stall as a cursory look, as a projection of what the mixing height should be in the fire weather planning forecast, and that's the zone. And so with that, they then massage it, because the forecasting offices that are along the coast, which are 3 for North Carolina, they notice certain things about how maybe stall is not performing as well as it should be, obviously because of the Atlantic Ocean out there. And so they make and tweak adjustments before they put out that fire weather planning forecast. But it was a good, pleasant surprise that they are looking at and trying to change their methods, because in North Carolina, we have 7 forecasting offices. And out of those 7 forecasting offices, they were using 4 methods to forecast mixing height. So from a user perspective, they were all over the charts. In other words, I'd be standing on a county line in one forecasting office and I could light it up and burn. But if I stepped over the county line because I was in a different forecasting office area, they had a lower mixing height and I couldn't burn. But the burner's looking up at the sky and going, what's the difference? And to me, there wasn't much of a difference. Either it was high or low. So again, there was inconsistency in their methods and their biases. And so at least, I guess with the effort of Matt Farron in North Carolina, they are taking to heart and looking at the stall as a starting point as they develop and move forward to put it out in that forecast for the burners or for the people dealing with wildfires. And I mean, that's only in North Carolina. I don't know how that has progressed in the other 50 states.
I'm going to suggest we wrap up at 2:30 with the group here in the recording. Any other closeout questions? Or, I mean, there's obviously, you have a very active interest in Gary here, and Susan. I'm sure they both would be supportive of any follow-up direct. And we can make sure the group gets that contact information as well, if that would be useful. Anything else from the group? From the team?
No, I think that pretty much covers it for now. Yeah, it'd be great to, as you said, have one or multiple of you as a potential resource to reach out to if we have some questions moving forward related to this sort of stuff. You guys, yeah, definitely have provided us with a lot of food for thought and also just some wonderful information that is hard to get, without talking to people that are doing it and people who have these jobs that you all have. So yeah, really appreciate. I know we all really appreciate your guys' time, and yeah, appreciate you all being willing to go over on this meeting here and discuss some of our questions as well.
All righty. Well, thank you very much for reaching out and intersecting with us. And and Dean and others, I don't know Tim Matthews' personal email address now that he has retired, but Robin likely will, would be my thought. We can track him down other ways. Others, our listing of contacts are on the NWCG SmoC Committee website. You got Gary's email address as well as Susan and my own. And my guess is the Fire Environment Committee might even still have Tim Matthews' web information up there as well. But you can poke around on the NWCG site and kind of go from there. So greatly appreciate this. As you can tell, we are interested for lots of different reasons in mixing height methodologies and the information that you put together. So good stuff. Thank you. Kudos. And the folks on NASA Develop, if you want to see more collaborations with the committee, let us know. We'd be lovely to collaborate further where the opportunity arises.